Hi, it's Chris. Welcome back to another episode of this tutorial chapter. Last time we had a brief look at the night sky for first orientation. This time we want to focus on following things. A. The nomenclature of important points on planes. B. The coordinate systems of the night sky. And C. Finding stars with their coordinates in both systems. And technical terms like azimuth or vernal equinox point should somehow be sorted out before you start your first session. I wish I had sorted them out on my first days, whatever. So, let's start with the night sky. So, this is a fisheye perspective of the night sky. We're on the ground looking upwards. So, first thing we get name in our shot is our horizon. Yeah, I told you we start from scratch. So the horizon is subjective to the observer and parting the sky into two parts. One can be observed right now and the other can't because it's below the horizon. The part you can observe highly depends on the time and your location. Second vocabulary is the zenith. It's the point right overhead and also subjective to the observer. And the third one is the meridian. This is a line crossing straight from north through the zenith to south. It parts the sky in east and west half. The meridian will become quite familiar to us because we need to reset the scope if stars move across it. More in later videos. So that was all relative to the observer. Different observers at different locations will see different stars near zenith or meridian. And so we started with the subjective perspective, the situation we as a beginner observer are most familiar with. And the night sky is not really a sphere, it's the eternity of space, but from us it looks like a hollow sphere with the stars pinned to the inside, and like nearly all of our ancestors thought it would be one. So if we take that projection perspective and see the stars projected into a hollow sphere, we can also locate them using a grid onto that sphere. Then every star has its own coordinate and you can refer to it. Taking the zenith, our horizon, and the north axis as a reference point, we can establish the azimuthal coordinate grid. And it has two axes. The azimuth, it's the angle from north, and the altitude. So in short, alt-az. And you can point at any star just by these two angles. And this grid is variable to your position and even the current time. We come back to that point in a sec. So, next thing we notice at the night sky is the movement of the stars. It's due to Earth's rotation, of course. And all stars, at least here in the northern hemisphere, seems to circle a point close to the North Star. The exact pole of rotation is called the North Celestial Pole, and that is the projection of the rotational axis of the Earth. We can use this celestial pole to establish another and even more important coordinate grid, the equatorial grid. You may notice the equatorial grid, we call it EQ grid from here on, is like tilted from our perspective, simply just because we are not at the true North Pole right now. And as you might guess, going down 90 degrees from the celestial pole will bring us to the so-called celestial equator. That's the projection of Earth's equator onto the hollow sphere. And this EQ grid is invariant to the observing point, meaning every observer will tell the same when talking about the celestial North Pole. And the celestial equator is the same too, no matter where you are. And like on the azimuthal grid, you can point to any star using two angles. One is the RA, say right ascension angle, given in caution, hours. Why that? Yeah, because the sky turns around every 24 hours. And so we say star A is 4 hours away from where star B is right now, okay? Just because it's handy. So RA is our turning angle and we're gonna need that later on. And then declination, that's simply the elevation above the celestial equator in degree. So there you have it. These are the two coordinate systems. Now we need to talk how to use them. First we look at the azimuthal grid and why it has flaws. So this is a random night sky. We want to search, say, Elliot. This is a bright star over the building. So first we need a reference point to start from. In Alt-As we choose north. Then you seek the first angle, the azimuth, to the right. That's just convention. And after doing so you point upwards in degrees needed. Easy, isn't it? Elliott simply has in Alt-As 21 degree, 56 minutes altitude and a 19 degree and 18 minutes azimuth. By the way, 0, 0, this is plain north at the horizon. Okay, and warning. 56 minutes? What? Okay, see. 1 degree is parted into 60 arc minutes and 1 minute is parted into 60 arc seconds. That's just the way it works. So 1 degree is 60 times 60 arc seconds. And now for Alt-As, where's the flaw? See, we said the azimuthal grid is subjective and not objective. Where's Elliott 1 hour later? It's on 55 degree 52 minutes alt and 27 degree 47 minutes as. What? It moved! But our coordinate system didn't, because we didn't. It's our reference frame, not Elliott's. So calling a friend in the middle of the night and telling him the old us coordinates of Elliott only won't give him any clues, unless he's your neighbor. And by the way, calling people at night just because of coordinate systems normally disturbs them, whatever. And that's where the flaw is. For doing so we need a reference frame attached to the stars, not to us. There the EQ grid walks right into the show. See, the EQ grid is fixed to the vernal equinox point, where the ecliptic, that's the Earth's orbit plane, and the celestial equator intercept. Then one axis is straight up to the celestial north pole, the other is the celestial equator. And by doing so, the grid is fixed to the stars, and if the sky, I mean Earth, rotates, so does the grid. The coordinates are moving from east to west in one night. And a star has always the same coordinate in the night sky, no matter where or when you are. That's the beauty of the EQ grid. So, it's then simple as this. You need to tell your scope where 0 hours on right ascension is. Then move along the celestial equator to match the right ascension hour angle, and then move the angle up in declination until you find, say, Capella. And Capella has RA 5 hours 60 minutes and DEC 45 degrees and 59 minutes, like always. Summer, winter, north, south, morning, noon, midnight, always. But for the beginner, double watch this video. It's a bit unintuitive first, but we need it for finding stars. Because all we do, take a list of stars, say an Astro pocketbook, and there are the RA and DEC coordinates for everyone. Canada, UK, Russia, everyone. And then everyone uses this reference frame, and then you can call your friend in the middle of the night and disturb him with coordinates of Capella, or don't. Either way, I hope you now have kind of a feeling for the main reference frames. It's very important to know what RA and DEC are, at least if it's for using your scope later on. And finding coordinates. Handhelds do this for you on computerized mounts, but you need to tell them and you should understand what they do, so that you can, for example, sort out errors. Next video will be about technical stuff like focal length and aperture, and we will finally approach telescope land, okay? If you like this video, don't forget to hit the like button. And if you know a person starting out with all this astro stuff right now, share this channel. May they here find their starting point for this great journey. So, like always, I say clear skies until next time here on Catching Photons.